Hello everyone, and welcome to HACSTFB number 2. I'm actually having quite a lot of fun making these videos, so this might be a weekly thing. But today the topic is going to be a lot more mathematical. It's going to be about probabilistic programming languages. And now maybe you've heard about differential programming languages. Those are the languages in which neural networks are usually implemented. Maybe you've heard of frameworks like PyTorch, etc. Well, today it's kind of about the reverse thing. It's about tools that use automatic integration as part of their suitcase, and those are probabilistic programming languages. And their main topic is also about probability, but I think it's a lot more closer to automatic statistics than, say, machine learning. For me, the entire deep learning space has a lot more to do with numerics than it has to do with statistics, and hopefully this video also convinces you maybe that there's a lot more to be explored in the area of probabilistic programming languages. But yeah, without further ado, let's just get started. To get started, let's talk about normal programming languages. So, if you remember, normal programming languages are kind of like a cookbook. They sequentially execute a command from the top to the bottom. And most importantly, the thing that we usually do operations on is what you call types. And the types in normal programming languages are numbers, such as integers, or strings, right? Okay. So, what makes probabilistic programming languages different? Well, instead of operating on types like numbers and strings, in addition to those types, it also introduces a new type, which is the probability distribution. Okay. So if you remember from statistics what probability distributions are, you might already get a sense of what these tools do. But if you have no idea or remember what probability distributions are, let's just go over a quick example. So this is a circle chicken problem. And in this problem, at some point, every chicken decides to either pick the right neighbor or the left neighbor with a probability of 1/2 each. All right? So for example, this chicken picks either the right chicken or the left chicken with a 1/2 probability. And the same happens for all chickens simultaneously. And the question is, what are the number of unpecked chickens at the end? And usually this question, the way it's asked is we're interested in what are the expected number of unpecked chickens. But let's say we're not only interested in the expected numbers, but we're also interested in, let's say, how often does it happen that exactly 1 chicken is unpecked or 0 chickens are unpecked. So the difference between expectations and probability distribution is that the probability distribution function tells you for each possible case what the probability is. So let's continue and implement this with probabilistic programming so you can get a grasp of how these tools work. Alright, so let's implement the chicken circle problem. And well, the first thing we need, and the programming language I'm using here, by the way, is Psi. So it's called Psi, and you can check it out at psisolver.org. It's a research language, but it already works pretty well. Alright, so so what can you do? So let's first create the main function. That's normal. And let's think about how many chickens we have. Well, we have 10 chickens, right? Now let's also create an array which contains all the pegged locations. Okay, so let's just say it's an array, and it has size n. And let's say it's filled by default with 0, which means it's unpacked. And to denote that it's not an integer but a boolean, let's just use this particular type. Okay, so, and next what we want to do is we want to start the pecking. So for each chicken, we start the pecking. So in mathematical notation, we loop through all the chickens from 0 to n-1. And now we select a place to be pegged. I'm indicating this with the 3 dots for now. We want to turn this into, well, a 1, right? And I forget to add the semicolons because I'm used to Python programming recently. But as you can see, this is a hole and I will insert more information here. But basically, I want to turn one entry and turn it into 1. So I want to make it from from being unpacked the chicken to being packed. Okay, so the chicken I, what will it select? Well, it will select either the left neighbor or the right neighbor. One way to implement this is I can say, well, I just select I plus if, and now we just flip a coin with probability 1/2, and if it lands on heads, well, we add 1 to the number, and if it lands on tails, we add -1 to the number. Now we have to be a bit careful because the chickens are in a circle. The 0th chicken can't pick the -1st chicken, but it wants to pick the nth chicken. So what we have to do is we have to compute this number modulo n. Right. So now we just pack the chickens, and now all that's left to do is just count the number of unpacked chickens. So this is again just like a normal programming language. We know the number of unpacked chickens is just an integer, and we can just use integers. We don't need probability distributions in here. And I can say, well, for I in, let's just go through the numbers, 0 till n. N is not inclusive. And the number of unpacked chickens is, we add, are the number of not picked chickens. All right, that should be pretty self-explanatory. The exclamation mark just means to negate this Boolean entry. Now I'm interested in the number of unpacked chickens. Okay, so let's just quickly quit this application and try to run it. So the way I run it is I just run psi, and now I use the script here, and I'm interested in the expectation. And now what I like to add is this DP claim, which makes the entire program work a bit faster. And the number of unpacked chickens are 5/2. Okay, so 5/2 is 2.5, so I would expect the number of unpacked chickens to be 2.5. That's kind of cool. So this kind of worked like magic. And well, how does this even work? So if we would approach this normally, well, what would we do? Let me find the keynote here. What we would do is we would just we would look at one chicken and think, well, what's the probability that this chicken is unpacked? And well, it's the probability that this chicken doesn't pick it and the probability that this chicken doesn't pick it, which happens with 1/2 probability here and 1/2 probability here. So together we now need to multiply these two probabilities because we don't want any of them to pick this chicken. So we end up with a probability of 1/4 that this chicken is unpacked. And now by this theorem called the linearity of expectation, we can apply this logic to every chicken, and we can just multiply this number 1/4 by the number of chickens, which are 10, to land at 5/2, which is 2.5 chickens. But I'm not just interested in, well, the number of unpacked chickens. Let's say I'm interested in what's the probability that none of the chickens get packed. And if you think about it, well, what's possible is it's pretty difficult. So you can say every chicken picks a right chicken, every chicken picks a left chicken, and then is there anything else which is possible? Well, let me think about this real quick. So for example, these two chickens can peck each other, 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 and these two chickens can peck each other. And then there's also an odd number, so like these two chickens, and then we can do this, and these two chickens, and then we can do the same thing, but with the different parity, where these two chickens peck each other, and these two chickens peck each other. And now I haven't proved that this is exhaustive, so, but I think this way you can reason about the number that there's no unpacked chicken left, okay? But instead of trying to reason about it logically, let's just use the program. And let's just go back to the magical program, and let's say we're just interested, well, what's the probability that there's 0 unpacked chickens, okay? So now I run this again. I'm interested in the expected value, and it tells me 1/256. Okay, that's cool. So let's continue. Well, what's the probability that exactly one chicken is unpacked? Well, it's 5/64. Okay, that's good to know. Well, what about, say, 2 chickens? Run this program again. Oh, it's 55/128. Interesting. Okay, and what's the probability that, say, 3 chickens are unpacked? It's 25 over 65. Okay, that's cool. What about 4? Run it again. 25 over 256. Okay, and let's just run it once more for 5. 0. Ha! Okay, so it's impossible for there to be 5 unpacked chickens. So why might this be? Let's go back to here and think about this problem real quick. Okay, so let me quickly try to at least think about how I would solve this. So in total there's 10 pecks, right? So how many pecks can a chicken take at most? Well, it can take 2 pecks. So in total we could have that exactly 5 chickens are pecked, okay? And therefore also 5 unpacked chickens. So from this argument, from the pigeonhole argument, this might seem to work. But so let's see if this precise case is possible. So there, from the pecked chickens, every pecked chicken has to take 2 pecks. So can this chicken take 2 pecks? Well, yes, let's say this guy and this guy. But now this chicken also has to peck one of those 2 chickens. So let's say it picks the chicken on the bottom. And now, well, we only have 1 unpacked chicken so far. And because this chicken also needs to take 2 pecks, it takes the peck of this chicken, okay? So now we have 2 unpicked chickens and 2 picked chickens. So far so good. Now we can do the same argument with, let's say, the next 4. And so now we cleared this argument for these 4 chickens. So now we can use another 4 chickens with the same argument, and we can say, let's say we take these 4 chickens, but now there's 2 chickens that remain, and they have to pick one of these unpicked chickens, so this doesn't work. But let's say there's we pick those 4 chickens instead. Well, now we have these 2 chickens, and well, this is supposed to be unpacked, and this is supposed to be unpacked, but now this guy needs to pick one of those 2, and again the property is not satisfied. And I think you can make some symmetrical argument with this, but I'm not going to prove it formally. Why? Well, we just proved it by using the probabilistic program. So the cool thing about using the probabilistic program is you don't need to use all these complicated reasoning arguments, okay? It just computes the probabilities for you. All right, so far so good. Now, another thing it can do is, let's say we're interested in the number of unpacked chickens which are less than or equal to 3. So let's say, what's the probability that 0, 1, 2, or 3 unpacked chickens remain? So let's run this program, and it tells us that this is 231 over 256. Now, there's another way to do this, which is, well, let's just say we're interested in the number of unpacked chickens, and instead of being interested in the expected value, let's just say we're interested in the probability in general. And as you can see, you kind of get this probability density function. Now, if you don't know what the probability density function is, that is fine. Just here you have this function called the direct delta. And the way you have to read it is, well, if we insert the number of unpacked chickens to be 0, then this function gives you a 1, okay? And if we pick the number of unpacked chickens and let's say it's a 3, well, then this direct delta is 1. It's actually not 1, it's infinity, and that has something to do with integration, but it's a bit too complicated to explain. So usually what you do is you're not interested in the probability density function, but instead you're interested in the cumulative distribution function, or the CDF, okay? So this is the CDF. Now, does it look a bit neater? No, not really, but at least there's no direct deltas in this function here, okay? And now if you're more comfortable with Mathematica output, you can just say minus minus Mathematica to get Mathematica output, or you can say minus minus Maple to get the Maple output. Okay, so I'm gonna explain what this means, but what you have to know is, let's just type in this function. In Mathematica. So bool is basically 1 if the inner condition is satisfied. So if negative n unpacked is less than 0, then this condition is satisfied. Okay? And if here negative n unpacked plus 4 is less than or equal to 0, then this condition is 1. So these are called Iverson brackets, for example. That's another way of calling them. So let's plot this function, and let's plot it from, say, 0 till 10, because there's 10 chickens, and we get this nice graph here. And let's say we're interested in a log plot. I think this works. Okay, so now you can see the log distributions as well. Now, I don't really like that it normalizes, so let's say I'm interested from -1 to 10. So now you can see it's 0 at -1, but there's a slight probability of 1 over 256 for it to be 1. So okay, how do I read this? This is the CDF function. So if I type in P of 3, it gives me the probability that there's 3 or less unpacked chickens. Okay, if we just evaluate it like this. So we can see it's 231 over 256. So let's just confirm this by modifying the code real quick. Let's say we're interested in the number of unpacked chickens which are less, the probability that there's not more than 3 unpacked chickens. Then I can just run this program like follows. I'm just going to add the minus dp function, and as you can see, it's 231 over 256. So this is just a generalization of this function. So let's say I'm interested in P of 2. I get the number of the probability that there's not more than 2 unpacked chickens. Same with 1 and with 0. And for 5, this probability is 1, right? Because we saw it's impossible for there to be 5 unpacked chickens. And equivalently, the probability of there being 5 or more unpacked chickens, well, it's 1. No, and the same with 4, actually. All right, I hope this wasn't too complicated, but if this was too complicated, maybe the next section clears it up for you. So basically, there's a whole duality to probabilistic programming languages, which is also the sampling-based probabilistic programming languages. So let's think about how we could implement our own such language. And a very easy way to do it is to simply simulate a lot of those programs. So if we looked at our code before, right, so this was the code. So what we could do here, and I'm just interested in the expected value now. If I look at this code, what I can do is I can simply just run this code once. I can flip a coin. I go through the code, and at the end I get a number of unpacked chickens, right? So I can just run this program many times, and eventually I get a distribution, right? So that's one way to implement such a probabilistic programming language. Now let's see how this would work. So let's just create one sample of chickens, right? And now each chicken has a pecking partner, let's say. And now let's count the number of unpacked chickens. Well, in this case, it's 3. So now we have in our first row, we have 1 out of 1 cases where there's 3 unpacked chickens and 0 in all the other cases. All right, let's do it again. So now, again, let's count the unpacked chickens. So can you see them all? Well, there's only 1, right? So now we have 2 samples, right? So now we have 1 where only 1 chicken is unpacked and 1 where only 3 chickens is unpacked. Okay, so let's do it again. We run this algorithm again, and now can you see all the unpacked chickens? Well, there's 2. Okay, so now it seems like it's quite a uniform distribution, right? So let's just run it again, and let's see, well, what are the unpacked chickens? Well, in this case, there's 2, right? And now it seems that 2 happens a bit more frequently, and so on and so on. And eventually, this process, at least in this particular case, will converge to the same solution as the exact solution. And this is a very, very important point, that there's basically 2 different types of probabilistic programming languages. There's the sampling-based ones, and then there's the exact ones. So the one I used before is an exact solver, while tools like Anglican and Turing and Stan are sampling-based. Now, the exact tools, when they work, they tend to always be better than the sampling-based ones, But if they don't work, and usually the expression might be too complicated to evaluate, well, then you have to just use sampling-based probabilistic programming languages. And then there's, of course, some hybrid methods, and so on and so on. But basically, and this is a very important point, is just because it looks like the solution converged doesn't actually mean that you have a correct solution. It might just be that suddenly you need like a septillion of operations to get an accurate distribution. And it's not at all clear how the convergence works in general. It just happens to work pretty well here on the chickens. All right, but enough about chickens, because I can't talk about chickens anymore, so let's just move on. And another operation that probabilistic programming languages have is the observing operation. So let's think about this. So what does it say? Here I create a Gaussian distribution, and starting from the observe operation, we only have probability distributions where x is larger than 3. So in a way, we kind of truncate the Gaussian distribution. And because we're in the field of probability, the area under the curve has to remain 1, right? So we also have to skew the curve a little bit, okay? But basically, what happens is we skew the probability and we condition it, conditioning is the right word, we condition it on x is larger than 3, and we get a new distribution. So in a way, there's kind of the hidden Bayesian rule hidden inside of it. And if you do exact probabilistic programming, well, you need to use Bayes' rule. Now let's quickly see how a sampling-based algorithm would look at this problem. Well, it could simply just create one sample of the Gaussian distribution, and whenever an observe statement is not satisfied, it will simply cancel that attempt, and it will not count it towards the total number of attempts. Okay? And probabilistic programming languages which are exact, well, they have to use Bayes' rule. Okay? So let's say you go into a bar and you have your probabilistic program with you, and somebody challenges you to a coin flip game. And now you kind of assume that the coin is rigged, right? But let's say you are under the assumption that, well, at least there's some probability p with which the coin always lands. It might be higher, it might be lower. You don't know the probability, but that's kind of what you want to figure out. Okay, so instead of picking out your notebook and starting to do some calculations, what we can also do is we can just simply use a probabilistic program. Okay, so let's do exactly that and switch to the terminal. All right, so let's get out of this program. And now let's create a new program, and let's call it coin.psi. All right. So we need a main function, of course, and let's call p the probability of the coin, well, the weight of the coin. And basically, with the probability p, the coin lands on heads. And let's say at the start we don't really know what it is. So let's say it's anywhere between 0 and 1. We just don't know what the probability is. Okay. And now let's also have some coin throws, which for now all we do is we just create an array. Okay. And we'll give meaning to that array in a bit. Okay. So we have this array of 1s and 0s. And next, now we want to iterate over these elements. r.length, and wait, I think I need to do it like this, because we don't want to include r.length. And right, now what we do? Well, we interpret these numbers as actual coin flips that happened. So we just flip a coin, and with what probability do we flip the coin? Well, we flip it with the probability p, right? We don't know what p is, but we just flip it with p. We can just do it as though we know p, and now we observe that the coin lands, well, it lands on r of I. So after doing this a few times, what this means is, well, the coin lands on heads, heads, tails, heads, heads, tails. So what do we know from all this? Well, what we definitely know is that it is impossible for the coin to always land on heads, and it's impossible for the coin to always land on tails. But what else do we know? this kind of seems a bit arbitrary because, well, everything else is still possible, right? But the probabilities change, and that's what's important here. So, of course, I forgot a semicolon here, but let's take this program and let's just run it and see what the expectation of this program is. Minus expectation, and we get 5/8. Okay, so we think the coin is rigged towards heads, towards 1. And we think on average the coin gets us a 5/8. So with this calculation, we can now go into this match, and we have some information now. We know that the coin is rigged, and we know by how much the coin is rigged, at least in expectation. It might still be that the coin is completely normal. So how can we see, well, what's the probability that the coin is completely normal? Well, fun fact, if you just say, well, what's the probability that p is equal to 0.5? Well, you can't really do this because we say p is uniformly distributed between 0 and 1, and it's kind of impossible for it to be exactly 0.5. So let's say, well, let's say this is fairly fair, right? So what's the probability that the coin is fairly fair? Okay, and oops, and this, it's not a Python. I'm wondering if it, okay, and we get this new probability distribution and this new probability, and that's a probability that it's still a fair coin, right? So it still might be that the coin is fair, we just don't know exactly. Okay. Now, I think this is a much nicer example to show you how to think about probability density functions. I'm not interested in the fair coin, I'm just interested in the coin in general. Okay, so let's run it again, and now we get this this polynomial here, and this is, and let's output it in Mathematica notation, and let's take this equation and put it into Wolfram Alpha. Okay, and now let's plot p of x and x in the range between 0 and 1, and we get this curve, right? And you can see it's kind of skewed towards heads, right? And the way you can interpret this is, well, I'm interested in a probability of the coin, right? And I want to know, well, what's the probability that the coin is weighed between 0.6 and 0.4? Well, what you do is you look at the graph, and then, well, you take the area under the curve between 0.4 and 0.6, okay? And it should also make now sense why it's impossible to ask, well, what's the probability that the coin weighs exactly 0.5? Well, it's always going to be 0, right? Because it might also be 0.5, 0.0001, right? And in practice, you can't really measure exactly 0.5. It just doesn't happen, okay? And so it's better to think in terms of areas, okay? And this is why we need integration. And so let's do the integration. And the integration is the CDF function. And this gives you, well, the area under the curve between -infinity up to that point. So let's call this function C, and let's plot this function. And the CDF, well, as we know, it goes from 0 to 1. We saw this previously with the chickens. And, well, this is how the curves look like, okay? So now if we're interested, well, what's the probability that the coin is somewhat fair? Let's say somewhat fair means it lies between 0.5 and say 0.47. Well, then we can just subtract these two values, and now we get the probability that it's a fairly fair coin. And, well, we still have like a 10% probability that it's a fair coin. So you can't really use this, for example, to prove that he's a charlatan, right? Because, you know, 10% happens all the time. But if you add enough samples, eventually this function should converge, okay? Now, you might be asking, well, why did you use a uniform distribution here? Well, let's say at the start I say, well, it's a normal distribution and it's centered at 0.5 with variance 1, okay? That might be another assumption you have. You might say, well, it's probably more likely to be at around 0.5. And sorry, we don't actually call it normal distribution, we call it Gauss. Now, this works, but then we have to be a bit careful, because when we start flipping the coin, the Gaussian distribution still has a non-negative probability for numbers below 0 or above 1. So a very easy way to fix this is we can simply state, observe that p is greater or equal to 0 and p is less than or equal to 1. So now we have a truncated Gaussian, right? So let's do this, and now, well, let's just see what the expectation of this program might be. So let's run this example, expectation, and yeah, there we go. And you can see it's already quite a bit more complicated, right? And I'm not going to try to read this output, so instead I'm going to use a Mathematica output. And here we go. So it still believes that there's a probability of an error, because, well, obviously there might be an error, right, if the coin is below 0 or above 1, but we observed that this cannot happen. So at least in theory, the probability of error should be 0. So let's open Mathematica and see if this is actually the case. Right. So I actually did this before. I just tested it real quick, and yes, indeed, the expectation has probability 0. The probability of error is 0. So now what we get is expectation under condition that there isn't an error, right? But because the error probability is 0, this is also the expected probability without an error. So I can simply take this number now and call it the expected value. As you can see, I tried this just before to make sure it actually works. And if I click on enter, we get this pretty complicated expression, right? And but one way we can evaluate these, at least in Mathematica, is I can just call n, which stands for numerically evaluate, and now I can use the expected value, and now I can say for how many digits, let's say for 10 digits, and we get that it's around 0.62243, which is actually quite close to the coin probability we had before. Just as a reminder, I think it was 5/8, but let's just run it again just to make sure. So uniform 0, 1, and yeah, it's 5/8, right? So of course now we can also numerically evaluate what 5/8 is, but I think I can also do this even myself in my head. So that's 0.625, and as you can see, these numbers are pretty close already, and this is something that I'm going to further investigate. So let's actually plot the two probability density functions next to each other. So let's take the PDF of the uniform distribution. So let's call it uniform PDF of x, and call it here. Oops, one F too much. And also define the uniform CDF. And we know how to generate that one because we did it before. Just paste it in here real quick. There we go. And oh, I should have used p like this, because now it's actually used as an argument. Otherwise it's not used as an argument. Mathematica has a bit of a weird syntax. And now let's modify the coin.psi file. And instead of using a uniform, let's switch back to the truncated Gaussian. And now let's actually try to get the PDF. And this is it. Now the probability of error still remains 0. I think I didn't run it, but I'm pretty sure it is. So let's call this the Gauss PDF of p. And well, it's this fairly complicated function. And oh, I did the underscore on the wrong side. And now also have the CDF, right? and that will be the integral of this function. And okay, the integral is already quite a big function, so just so you have a sense of how big the function actually is, it's this function here. So basically, I'm not sure if if Mathematica is able to integrate this function here, but basically the integral of Gauss PDF should be this function. And there we go. All right, so let's compare the two plots. So let's plot CDF, the uniform PDF of x with x between 0 and 1. And let's also plot the Gauss PDF of x between 0 and 1. And as we can see, these two functions are already very, very similar, even though they have completely different assumptions on the coin. And well, for completeness sake, let's also quickly plot the integrals of both functions. So this is the integral of the uniform distribution, and this is the integral of the Gauss distribution. Oh, it seems to take a while to compute the Gaussian integral. But okay, they are equal, or they look very, very close to equal. And that's no surprise, that's no coincidence. This has a bit to do with the law of big numbers. Basically, as long as, whoops, what just happened? I have a black screen here. All right, let's zoom in here. So as long as this probability distribution is positive for whatever real distribution at the end of the day the coin has, it will eventually converge to that number. And it will converge to that fairly quickly, and it doesn't really matter if you use a Gaussian distribution here, or a truncated Gaussian or uniform distribution. With enough samples, you will get similar looking probability curves. All right, so that was that. And now I'm more or less finished. I hope this inspired you to look at probabilistic programming yourself. I think on the slide I have, well, one more example, which is a Monty Hall problem. And here I just ask you to maybe implement this for yourself. I think it's a nice problem. If I'm sure you've heard of it, and it's like it's really a problem that makes you understand the observe function a lot better. So if you're not 100% confident how the observe function works at the moment, if you implement the Monty Hall problem yourself, well, then hopefully it should become fairly clear. And of course, there are many other probabilistic programming things you can do. For example, Pyro combines deep learning with sampling-based probabilistic inference, and so on. Maybe another example that I can quickly mention is the multivariate Gaussian. So let's say you have a few points, you have a data set, and you assume they're modeled by a Gaussian, right? Which means they're just modeled by these point clouds, right? So you think it's generated by a point cloud. Now, how can I get the standard deviation and the centers of those Gaussians? And it's actually quite easy. This has nothing to do with Gaussian mixture models at the moment. It's just to figure out where the point is. But imagine you have well, you have two Gaussians, and you're trying to figure out, well, what are the centers of those two Gaussians and what are the standard deviations of those two Gaussians. And then if you think about it, well, you can just sample uniformly at first the centers and the standard deviation, admitting that you don't know what the center and the standard deviations are. And then later, now we have A and B, which are, well, those are the Gaussians, and we don't actually know them. And then for each point in the dataset, for each point target pair in the dataset, we will sample a point. Say if the target is from A, we will sample from A, and then observe that the sample is actually equal to the point. And through this observation, the probabilities should get updated. Like So it's a very Bayesian thing. Basically, we condition on the fact that the sample is equal to the point, and then we deduce from that, well, what's the probability of the center, or what's the probability of the standard deviations, given that the sample equals to the point. And at the end, we return that distribution over those 8 variables, and you're probably interested in the expectation of those values, and then you get a close approximation to the real Gaussians. All right, and I can go on and on and on, but again, I think it's a nice place to stop. Again, this video didn't really take a lot of effort for me to do. I didn't really prepare a lot, and maybe it shows, but I still hope it's useful. And if not, that's okay to write. And maybe I'll do this a weekly thing, because I actually enjoy talking about tools like this. And well, who knows? Next time I'll probably do something more creative again, and then the time after that maybe something more mathematical again. But it's all about tools, and I hope that you are inspired by these tools to write your own tools, because we need more tools, and yeah, the world has a lack of tools, unfortunately. All right, see ya.